We are now moving into the next chapter, chapter 6, but before we go ahead and do that, we want to review a little bit from the very end of chapter 3 where we introduced the idea of bivariate data or two-variable data. So here we have 3 different scatter plots, and we want to state the type of correlation using directionality and strength. So go ahead and pause the video and state the type of correlation for all 3 of these scatter plots. So for the first one here, we have a pretty strong negative correlation. It's downtrending as the independent variable increases, the dependent variable decreases, and it's pretty linear, so I would say strong negative correlation. The second one, I would say weak to no correlation at all. It's pretty cloud-like. There's not really any trend to it. And then this last one, it's positive, and I would say moderate. There's not a whole lot of data points, possibly weak, so somewhere weak to moderate positive correlation. So lesson 6.1 is diving more into correlation and specifically measuring correlation quantitatively. So I would pause the video and write down these vocab words. So first one, a functional relationship, a formula or a function that we've been talking about for years exists that relates one variable to the other. All the data points lie on the same line or the curve, and that curve is the graph of the formula. A statistical relationship may not be such a direct relationship, but when they plotted, they can indicate some kind of tendency. So the first one, the functional, is like I give you a function and this is the relationship. Statistical is more like a scatter plot where you might be able to create a formula that models it, but it's not perfect. It's statistical. Linear correlation, so the data points lie close to a line. We can model them with a line. Nonlinear correlation, they might be modeled better with something else. Quadratic or sinusoidal, something along those lines. A perfect correlation would be something that matches a curve exactly. That's probably not going to happen in the real world unless it's a very specific experiment, but more likely you're going to have maybe close correlations, but probably not perfect. And then something we talked about at the end of chapter 3, correlation does not necessarily imply causation. Just because 2 things are related to each other doesn't necessarily mean one causes the other. So diving a little further into correlation versus causation, we have 4 statements here. Go ahead and pause the video and decide whether these statements are true or false. So for the first one, IB grades achieved by a student are an effect of the predicted grades given by their teachers. No, there's definitely correlated, but if I give you a predicted grade, that's not going to them turn around and say, okay, that's going to be your actual grade for IB. But again, they're correlated, but there's some other cause. Most likely, the student's ability is affecting what the predicted grade the teacher's going to give is, and that will also affect the IB grade that you achieve. So there's another factor that is affecting both of them that's creating this relationship. Second one, height of a person is a cause of their weight. I said true on this one because of the word a. Somebody who has more height is going to have usually more weight. Not always. There are other factors that go into effect. If this had been the cause of their weight, I would have said false. The book says false for that reason, but for me, I argue it is a cause. Somebody who is taller is going to have more mass than somebody who is shorter. So it is a cause, but it is not the cause. There are other factors that affect it. The next one, the number of ice creams sold is a cause of high temperatures. False. Buying an ice cream cannot affect the weather. There's definitely a correlation. It might be, the causation is probably actually the other direction. High temperatures would affect the number of ice creams sold. So the causation probably goes the other way. And then the last one, smoking is a cause of lung cancer. Yes, that's been proven, so that would be true. So again, correlation does not necessarily imply causation, and you also have to be careful in the direction of your causality. One way that we quantitatively measure correlation is by Pearson's product moment correlation coefficient, which we represent with the letter R. It's a measurement of linear correlation. We don't use it for nonlinear. And this variable R, it ranges from -1 included up to +1 included. And so here's just a couple examples. So if we have this here before, if we describe this qualitatively, we would say this is a weak positive correlation. Well, now they're telling us that this correlation coefficient is 0.3. On this one here, before qualitatively, we would describe it as a strong positive correlation, well, now we're saying quantitatively it's a R equals 0.9. And then the last one, moderate negative correlation, and they're telling us that this is R is equal to negative 0.6. The way that we calculate the correlation coefficient is equal to S sub xy, which is the covariance of x and y, and then divided by S sub x times S sub y, which are the standard deviations of your x and y coordinates. In this class, you will always just use a graphing calculator to calculate your correlation coefficient, but this would be how you would do it by hand. So we have here a little table that how we describe them quantitatively and how that applies to our qualitatively. So here they say the absolute value of R. That's because a positive versus negative correlation is just like what we talked about when we were talking about it qualitatively. So if you have a negative correlation, it just means you have a negative slope. As your independent variable increases, your dependent variable decreases. And then if you have a positive correlation coefficient, that just means there's a positive correlation. So as your independent variable increases, so does your dependent variable. So if your absolute value of R is very close to 0, so between 0 and about 0.25, we say it's no correlation or very weak correlation. If it's between 0.25 and 0.5, it's a weak correlation. If it's between 0.5 and 0.75, it's a moderate, and if it's above 0.75 up to 1, it's strong. Think of it like a percentage. So 1 would be like there's 100% correlation. 0.25 would be like there's a 25% correlation between these two variables. So kind of think of it as a percentage. Outliers, we talked about outliers back in chapter 3 and how we can calculate your outliers. So if you identify any outliers, you can kind of take that into account and decide whether or not you're going to utilize them. That's also something when you are looking at data that somebody else is presenting to you that you have to look at. So if they're talking about something and there's this huge outlier, did they include it? And is that affecting their results, or did they not include it? Does that affect their results? So that's part of the analytical side of the statistics.